This is part 2 of an ongoing series dedicated to explaining the classification of stars and the various star types within each class of star. If you haven't watched part 1, I'd recommend pausing this video and watching that first. In this video, we'll be looking at main sequence stars, also known as dwarf stars. These are the most numerous stars in the universe, and it includes our own star, the Sun. The red dwarf is the first star we'll be looking at. Red dwarfs are the smallest and coolest main sequence stars. They are also the most common stars in the universe. They aren't luminous enough to be seen by the naked eye from Earth, however, despite being so widespread and making up 3/4 of the stars in our own galaxy. Red dwarfs are M-type stars, which means that they have surface temperatures ranging from 2000 to 3500 Kelvin, or about 2300 Celsius. Like any main sequence star, the red dwarf creates heat and light by fusing hydrogen into heavier elements such as helium. Their small sizes and dim luminosities have come with their own advantages. For example, a red dwarf star will continue the process of fusion for 80 billion years, with some smaller red dwarfs potentially having lifespans of trillions of years. This means that every single red dwarf that is formed at the beginning of the universe is still alive today, with plenty of internal hydrogen supplies left to keep it going. Red dwarfs will also never enter a red giant phase in their lifetimes. The reason for this will become evident once we explore the larger main sequence star's internal processes. Instead, at the end of its life, the red dwarf will turn into a blue dwarf star as it gets hotter and its surface color turns blue. Now, if you remember part 1 of this series, you'll remember me explaining how the name given to star types has little to do with their actual color. For example, the brown dwarfs we covered in the last episode are actually reddish to purple in color. And red dwarfs, despite their name, are in fact yellowish in color in real life. We might actually be rare. And I don't mean life itself being rare. I mean life orbiting stars like our Sun. Planets orbiting red dwarfs actually have the highest chances of containing life. The reason for this is quite simple. This is because red dwarf stars have incredibly long lifespans, longer than any other main sequence star. If the orbiting planet is close enough to the parent red dwarf, and it has the right planetary conditions, life has the highest chance of forming on them. The closest stars to Earth are actually part of a system called Alpha Centauri, and this star system consists of 3 red dwarf stars with planets orbiting one of them, which is typically where we suspect life may be. The star system's only 4 light years away from Earth, so it's pretty close, but even so, we still can't see it with our naked eye. Yellow dwarfs are G-type stars, 0.84 to 1.15 solar masses. They have surface temperatures ranging from 5,300 to 6,000 Kelvin. There are also orange dwarf stars, which are the intermediate stage between a red dwarf and a yellow dwarf. I'll leave them out of this video just to avoid overcomplicating things, and because they're not that different from yellow dwarfs. Just like the red dwarf, yellow dwarfs are fueled by fusion in their cores. However, unlike red dwarfs, yellow dwarf stars will pass through a red giant phase in their lifetimes. This is because yellow dwarf stars are inefficient and only burn 10% of the hydrogen in their cores. Meanwhile, red dwarfs are much more efficient and the convection occurs throughout the entire star, using all the hydrogen efficiently. As a yellow dwarf star burns through its hydrogen supplies, they'll start expanding enormously and its surface temperature will decrease, forming a red giant star. The outer layers of this red giant will eventually shed away, and a white dwarf will be left behind, a small, compact, hot ball of electron degenerate matter. But we'll get into those types of stars in a later video. Now, as you may know, our Sun is a yellow dwarf star. This doesn't mean it's yellow in colour, however. There are some yellowish yellow dwarfs, but our Sun is white in colour due to its surface temperature. The only reason it appears yellow during sunsets and sunrises is because our atmosphere scatters blue and violet light rays. However, if you were to view the Sun in space, it would be bright white. Yellow dwarfs like our Sun have a lifespan of around 10 billion years until they reach their red giant phase. We are halfway through our Sun's lifespan, and the Sun will only continue to get hotter and brighter before using all of its hydrogen up. Now, if you went back about 4 billion years, near the beginning of Earth's lifespan and the beginning of our Sun, it would have been much cooler and dimmer, which explains why Venus probably had liquid oceans back then and Earth was a frozen ball of ice, at least until its atmosphere was thick enough to actually contain heat. But as the Sun got hotter and hotter as it aged, Venus began experiencing irreversible global warming, and it ended up being the planet it is today, a hot hellscape. Yellow dwarf star systems are somewhat likely to host planets with life, as we know because we're in one, but they're a lot less likely than a red dwarf due to yellow dwarfs not being anywhere near as stable. However, yellow, orange and red dwarfs are not the only types of main sequence star. There are also hotter, more massive hydrogen fusing stars out there. These are F-type stars, A-type stars and B-type stars, with F-type being slightly hotter and whiter than our Sun, and B-type being some of the hottest stars in the universe, with surface temperatures of 10,000 to 30,000 Kelvin. These stars are bright blue in colour, and are about as massive and as hot as main sequence stars can get. These large main sequence stars have slightly shorter lifespans than our Sun, and aren't likely to host planets with life, as they are quite unstable and have unusually strong stellar winds. And these are also the same stars that form supergiants and hypergiant stars when they die, but we'll get into that in a later video, of course. Alright, so that's the end of part 2 of the star classification series. If you enjoyed, drop a like, and part 3 should be released soon, and part 3 will be on supergiants and giants. Also, I'll be making a second channel, and this channel will be used for just random miscellaneous videos, possibly even a bit of gaming, who knows. But yeah, thanks for watching, and don't forget to subscribe. You better subscribe.